Hello, everybody. I'm Leonard from Haize Labs. First off, super excited to be here, and just want to give another round of applause and big thanks to Karan and the whole Nouscon team for organizing this. This has been an amazing experience meeting everybody here so far. Cool. So as Karan mentioned, we are Haize. We are known as maybe you guys know of us as the red teamers, the automated red teamers. And I'm here to show you today some of the fun stuff we've been working on, in particular taking a deep dive at one of the more recent attack methods we've developed. So first of all, what is Haize? Well, Haize has many connotations to it, but the real meaning of Haize is to red team and stress test, and more specifically, to rigorously test an LLM and agent with the explicit purpose of discovering all the failure modes before production. I think we all know this. Outlines is a great example of, like, right now there's a lot of kind of sloppy and like neural network stochastic soup going on. And we're all trying to add a little bit more structure and a little bit more concreteness to developing AI apps. And I think one way to do this is basically to constantly averagely test your system to try and figure out these failures before these occur out in production. So recently, we actually red teams. We had access to O1 ahead of their big launch last week. And we were featured as one of the big external red teaming organizations playing around with the safety values and human alignment of their system ahead of time. So there's some fun links here if you want to check it out. It's a much deeper dive than what I have time to cover today on some of our automated attack methods and what exactly we're trying to test for. And there's also a bunch of other things on our Twitter and social media and GitHubs if you want to check that out. We have a very exciting video of a lot of our comprehensive attacks across images and text and audio and coding and web agents and so on and so forth. Basically, we can test for any modality in, any modality out. Now, some of the different attack methods that we consider are evolutionary-based methods. If you guys are familiar with DSPy, we're big fans of DSPy for red teaming. We do gradient-based methods, in particular using gradients to inform which sort of coordinates we want to swap on our input prompts. We do various methods of tree search and MCTS for multi-turn jailbreaks. We're training our own VAE so that we can search over the latent space to basically bound and constrain our search to all the sort of domain-relevant context that might matter for a certain customer's application. We have really good LLMs as a judge because we need good signal to basically optimize with respect to in our attack methods, and a whole bunch more. But for the purposes of today's talk, I'll be talking about endless jailbreaks with bijection learning. So this is a bit on the nose. We call it endless jailbreaks because we are essentially teaching language models new languages at inference time. And you can basically teach language models any arbitrary language you'd like. And so there's essentially endless ways to teach language models these attack vectors and basically encode harmful queries in this new language. So some things to call out. Basically, our attack method is fully automated. It is universal up to a very strong degree. And it also exhibits this really curious property, which is there's like an inverse scaling law. The more powerful and capable your underlying model is, the more vulnerable to our attack it becomes. And we have a blog post if you want to check out our blog post on the Kira code. Our archive preprint has now been sitting in the depths of user moderation, archive moderators for the past 3 weeks. So I don't know when exactly that's coming out. But in the meantime, you can check out the blog post in the GitHub. OK, so quick TLDR. What is bijection learning? Why do you want to learn bijections in particular? The idea is if you've seen a bunch of cipher-based and or like low-resource language attacks, you can sort of get around model safeguards by basically shifting your inputs into like an out-of-distribution, well, out-of-safety fine-tuned distribution in capabilities distribution set of languages. So this might be, let's say, some low-resource language or some like base64 encoding or cipher encoding or something like this. Our idea is, OK, like models are getting more and more powerful. Instead of relying on known languages, why don't we just like teach them languages on the fly and see what happens, right? And so there are actually some like pretty simple bijections you might be able to consider. You can consider like swapping characters to random tokens. You can consider mapping characters to whatever digits or characters to other characters, permutations. The interesting thing, though, and something that actually matters a lot, is you can control the complexity of the language that you're learning. So by just basically changing the number of fixed points that you have in your language, you can directly, very smoothly parameterize the difficulty of the language. And this does matter a lot based on what model you're trying to attack. OK, so the setup is actually just like stupid simple. I chose this because it's like a really cute. I chose this for this talk because it's a cute and like bite-sized idea that I think people will enjoy. But the idea is, OK, we'll just ICL prompt a language model with a bunch of examples of translated text from English to whatever language we're trying to learn. Then we'll basically have a bunch of practice conversations in just the encoded language that the language model is supposed to get on distribution for. to actually send a jailbreak to the model, we'll encode a harmful request in this new language, pass that encoded request to the model. The model now knows how to perform this new language, and it'll respond back in this new language. And then critically require this bijection property, because we can then directly invert the response of the language model back into English. And there you just pretty easily, you are able to get a harmful response from the language model. Now, there's a lot of interesting properties about this attack that we'll explore in the later slides. But worth pointing out explicitly is that this works against an underlying model. But it also works against like a compound system of models. So even if you had like an input-output filter on your system specifically trying to target and defend against jailbreaks, this particular attack would still get past it, right? Because the input-output filters are only going to be as capable at detecting jailbreaks as the underlying model is going to be. And if we can get past the underlying model, we can also get past the input-output classifiers. OK, so bijection learning is super powerful and super automated. In fact, we can get close to 100% ASR on industry standard, or I guess I should say academic standard data sets against the safest models. So we can get 94% ASR on Claude Sonnet, 92% on Haiku, 94% on Opus. Same is true for HarmBench, which is another big academic data set. So not surprising, I wouldn't be showing this if it didn't work. But it turns out that we can basically choose random bijections, and this sort of thing just always happens to work, as long as you choose like the right complexity of fixed points to go after. OK, interestingly enough, language models are also all vulnerable to the same bijections in the same way, which is not expected a priori. And what I mean by this is we can literally just take the same bijection language and just throw it across all sorts of intents, harmful intents. You can encode basically any harmful request in this new bijection language, and you're able to get past all the defenses of a model pretty easily. We, of course, compared to Pliny the Prompter, who is the only legitimate guy making universal jailbreaks at this point in time. The other research out there is not so good on this. But as you can see, it's better. It's at least as good, if not better, than Pliny's jailbreaks. OK, so something that is worth highlighting as well is we were able to, or I mentioned that we're able to explicitly control the difficulty of the language using the fixed size, right, as I mentioned in the previous slides. And the reason this matters is that complex languages are harder to learn, but this also means that they're harder to defend against. There is a pretty delicate trade-off between nerfing the defenses versus nerfing just pure capabilities, as we'll see in a few slides. But first, I just want to point out that as you increase the number of fixed size points, i.e. as you make the language that you learn easier, you're going to fail a lot less. So I don't know if you can see this very clearly, but basically the red and yellow and orange is failure cases where the language model under attack is not able to actually perform any sort of reasoning at all. So it's just literally spouting gibberish because it's not able to learn the language that's we inserted in ICL. As you make the language easier, it's obviously able to learn the language, but of course it's refusing a lot more. Green means refusal in this case. We also benchmarked with MMLU. This is just variation on the same idea, i.e. like the easier the language, the better the model is going to perform in the core capabilities, right? So if you go from fixed size of 10 to 23, your MMLU score goes up across the board for all models, unsurprising. Right, basically at fixed size 26, you're basically just operating in English. So you'd expect to recover the full capabilities at that point. OK, but what is interesting is, as I mentioned, nerfing the capabilities of the model also tends to nerf the defenses, right? And so there's this sort of sweet middle spot where the complex language obfuscates the threats without obfuscating the actual capabilities too much. As you can see down there, this is conditioned on getting past the language model reasoning. So if the language model is actually able to spit out something that is coherent, it does actually produce a harmful response most of the time when you have a more difficult model. This is less true as you get to pure English. OK, but this is the real point I want to make. There is a sweet spot for bijection learning in terms of how complex the language is, right? As we saw earlier, harder languages degrade defenses and capabilities too much to the point where the model is not even responding coherently at all. But if you have too easy a language, then the model is capable of actually siphoning out and/or learning some sort of spurious correlation to determine that the input is harmful. In the middle, though, in terms of language capabilities or language complexity, there's a sweet spot in which the model is just confused enough that its defenses are tanked, but its capabilities are not tanked. Right? So this is around the 50-60% MMLU score, where the size of the data point indicates how difficult the language is, right? And so right in that middle, 50%, 60% MMLU, we're able to preserve a good amount of capabilities, but still have pretty high attack success rate, anywhere between 50, 70, 80%. Interestingly enough, this is not a point that we explored enough in this particular blog post, but there is an inverse scaling law where more capable models are more vulnerable. So if you look at each of the parabolas going up higher and higher, each of these is a larger model. So it goes GPT-4o Mini, GPT-4o, Claude 3 Haiku, and then Claude 3.5 Sonnet. Each of these are better models, larger models, and more capable models. And as you can see, the MMLU score is more or less the same horizontally, but the apex, i.e. the peak vulnerability, is higher and higher the more capable the model is, which we think is a pretty cool, pretty neat threat vector. Awesome. Well, so that's that for endless bijections. I should call out that we are now hiring for really awesome members of technical staff. We are based in New York City, not in SF. So if you want to come to New York, we are probably one of the only options you have in New York City. We have some pretty cool customers, including OpenAI, Anthropic, AI21, YouTube, Martian, DeepMind, some other big guys. We have some money in the bank, too. We just did our seed round led by General Callis earlier this summer. And most importantly, there's a lot of really fun work to be done, including a lot of optimization, interp, safety, security, PL, and systems work. So that's that. Our jobs page is up there, and then our Twitter page is down below. Thanks, guys.